This is my oral presentation at conference named CLEO Pacific 2022. The presentation name is Fabrication Technology of Low-Loss Plasmonic Waveguide, containing both plasmonic-friendly and plasmonic-unfriendly metals. In the presentation, I will talk about the reduction of optical loss for surface plasmon, and particularly about the choice of metal for plasmonic device. I will explain you about the misconception that there are plasmon-friendly metals like gold and plasmon-unfriendly metals like chromium. At first, I would like to remind you why we need plasmonic devices for optical integrated circuits. The first reason is because the size of plasmonic devices is very small. A typical length of plasmonic device is about 10 micrometer. As a result, a dense optical circuit can be fabricated with a lower cost and better functionality. Secondly, because a plasmonic device is very fast, the operation speed of 170 GHz has been demonstrated and is still very far from the speed limit of plasmonic devices. Plasmonic device is very fast because they are very short and they do not have the problem of the phase mismatch. Next, I will talk about the reduction of propagation loss of surface plasmon, a choice of metal. A metal absorbs light and therefore the propagation loss is unavoidable for surface plasmon. However, when design and fabrication technology of plasmonic device are optimized, the loss due to the light absorption by metal is negligibly small and does not degrade plasmonic device. Still, the optical loss is the key issue for any plasmonic device and should be carefully addressed. Since in a plasmonic device light is absorbed by metal, the choice of metal seems to be very important. At present, gold is the first choice as a metal material for a plasmonic device. Now, about 95% of plasmonic devices are made of gold. The gold has a yellowish color, in fact, due to plasmonic absorption. The gold looks as the best choice for plasmonic devices. However, from a technological point of view, gold is not a good material. It has a poor adhesion with other materials and a large diffusion coefficient. Today I will discuss whether other materials can be used for plasmonic devices instead of gold. I will show that with some structure engineering, these metals can be as good as gold for plasmonic devices. There is a misconception that there are plasmon-friendly metals like gold, aluminum and copper, because the absorption of light is weaker and only they should be used for a plasmonic device. And there are plasmon-unfriendly metals like cobalt, iron, chromium, because the absorption of light is much stronger and this metal should not be used in a plasmonic device. This figure shows the calculated propagation loss of light propagating in the bulk of metal using optical constant measured by Johnson and Christie. In fact, the absorption loss of plasmon-friendly metal is larger than in plasmon-unfriendly metals. The smallest absorption is in plasmon-unfriendly chromium, red line, and the largest absorption in the plasmon-friendly aluminum, pink line. This figure shows the calculated propagation loss of surface plasmon propagating along metal-silicon interface. Please notice the difference of used units. The absorption of plasmon is always substantially smaller than the absorption of light propagating in bulk of metal. Indeed, the gold, aluminum, copper have substantially smaller plasmon propagation loss of about 1 decibel per micrometer at wavelength 1.5 micrometer. For example, in case of a 5 micrometer long plasmonic device made of these metals, the insertion loss due to metal absorption is about 5 decibel. It is still large, but could be acceptable for some applications. In contrast, plasmon propagation loss is huge. About 20 decibel per micrometer is in plasmonic structure containing iron, cobalt, and chromium. Even in 1 micrometer long plasmonic device, near all light is absorbed in these metals, and therefore such plasmonic structure cannot be used in photonic integrating circuit. So, is it true then about the plasmon-friendly and unfriendly metals? In order to answer this question, it's necessary to understand the reason why the absorption of plasmon and the light absorption in the bulk of metal are so different. This figure shows the relative amount of optical field in metal. In the case of iron and chromium, there is a large amount of optical field of about 5% inside of metal. In contrast, the amount is less than 0.5% in case of aluminum. That is the reason why the plasmonic absorption is substantially smaller in the aluminum in comparison to the iron and chromium, despite the bulk absorption in aluminum is substantially larger. It is not only the bulk absorption by a metal, but also the refractive index of the metal determines the absorption of a surface plasmon. This figure shows skin depth in metal, and this figure shows the penetration depth of optical field into the dielectric. Both the smaller skin depths in metal and larger penetration depths into silicon are reason why the relative amount of light penetrating in aluminum is much smaller than that penetrating in iron and chromium. Next, I will talk about how to engineer a small propagation loss of surface plasmon. The amount of light penetrating into the metal can be engineered and reduced in more complex plasmonic structure, which contains more dielectric layers. For example, when a very thin silicon dioxide layer is inserted at the silicon metal interface. This figure shows the calculated propagation loss in plasmonic structure versus thickness of the inserted silicon dioxide layer. For both the plasmon-friendly and plasmon-unfriendly metals, the propagation loss can be reduced down to 0.01 decibel per micrometer at optimum silicon dioxide thickness. The optimum silicon dioxide thickness is different for each metal. Such loss means that for 10 micrometer long plasmonic devices, the absorption loss is only 0.1 decibel, which is negligible in comparison to the unavoidable coupling loss. I would like to emphasize a very important fact, which can be concluded from this figure, that plasmonic loss can be equally small for both the plasmonic-friendly and plasmonic-unfriendly metals when the plasmonic structure is properly engineered and optimized. This figure shows the percentage of light penetrating into the metal as a function of silicon dioxide thickness. At optimum thickness, the penetration is the smallest. These figures show the skin depth and the penetration depth in dielectric. If skin depth in metal is practically independent of silicon dioxide thickness, the penetration depth in dielectric increases substantially. It is the reason why the percentage of optical field in metal decreases with silicon dioxide thickness. Next, I will explain how much the propagation loss can be reduced. Even so, theoretically it is possible to reduce the plasmonic propagation loss to an ever small number. There are technological limitations which limit the possible reduction. The first limitation is the fabrication precision and roughness of the thin inserted dielectric layer. As you can see, the required fabrication precision is more severe for chromium, iron, and cobalt than for gold, aluminum, and copper. The line is steeper here. Another technological limitation is the penetration depth of optical field into the dielectric. It should not exceed about 10 micrometers. Otherwise, the plasmonic properties may become dependent on inhomogeneities and imperfection of the substrate. It limits possible reduction of about 0.01 decibel per micrometer, at least for these metals. This slide shows the result of experimental measurement. Light is coupled from input fiber into a silicon nanowire waveguide and next into the plasmonic waveguide. Passing through the plasmonic waveguide, light is coupled again into the silicon nanowire waveguide and finally into the output fiber. This is a top view. This figure shows a measured fiber-to-fiber transmission for different lengths of plasmonic section. From this, the transmission loss increases with the length of plasmonic section. From this dependence of transmission on the length of plasmonic section, the propagation loss of surface plasmon is evaluated to be 0.7 decibel per micrometer. The loss extrapolated to the zero length of plasmonic section gives a coupling loss between plasmonic and silicon nanowire waveguides of 4 decibel per facet. The propagation loss is still above theoretical limit, but is sufficiently small for an application. For example, the achieved plasmonic loss in plasmonic structure containing plasmon unfriendly cobalt is smaller than plasmonic loss in conventional gold dielectric plasmonic structure. In conclusion, details of technology for reduction of propagation loss of surface plasmon were described. The technology allows fabrication of low-loss plasmonic structure using both plasmon-friendly and plasmon-unfriendly metals. A small propagation loss and moderate coupling efficiency for cobalt-based plasmonic structure was demonstrated.